In this video, I'd like to discuss some mental shortcuts that you can use when solving some problems. So I'm going to talk about specific problems. For instance, let's say we have a question about powers. So let's say in that question we have something like 2 to the power of x squared plus 1 and then times 4 to the power of x squared minus 4 divided by 16 to the power of x cubed plus 2x. What's the mental shortcut here? What's the signal? Well, we have 2, we have 4, we have 16. This is a signal that we will use powers of 2. So 2 to the power that we have over here. I'm not going to solve it, I'm just showing the method, what is the shortcut. And then 4, we write it as 2 to the power of 2 to the certain thing, x squared minus 4. And then 16, we write it as 2 to the power 4, all of it to that power. This is the signal in the mind. Whenever we have something with similarities, for instance, powers of 2, write that down, because later on we could say 2, we group up the powers, and then we have a nice fraction going on. So that would be one case. Let's say, what else can we use? We can use the logarithmic properties. This is also very useful. So ln of x to the power of a, basically ln of something to a power equals to that power times the logarithm, and this is the most common property of logarithms that we're going to apply. And let me show you right now where is the most commonly applied, and that's usually applied in derivatives of x to its own power. For instance, we have an example as x to the power of x derivative. How can we solve this? Well, we do it by making a new function, y equals to x to the power of x, and we take the logarithms of each side. So ln. Now we can apply the logarithmic property that we just discussed. Basically, we'll take the power down. So we have ln of y equals to x times ln of x. And from here we can solve. From here we can differentiate each side with respect to x. Again, I'm not going to finish it off, I'm just showing the method that whenever we have x to the power of x or x to any power of itself, basically we have the control, the variable of interest, x to the power of x, x to the power square root of x, square root of x to the power of x, such examples, and we want to differentiate them, we make them a new function, logarithm, apply the property, and go from there. Now, what else can we talk about? Let's talk about continuity and differentiability. What's the mental signal there? So let's say we have a function f of x equals 2, and here we have x squared minus 2x plus 4 when x is less than 1, and let's say the other shape of the function will be x cubed plus 2x plus 3 when x is greater than or equal to 1. Now they're gonna ask you, for instance, when is this function continuous? Well, we know that it's continuous when we don't have any gaps in the graph, when we have defined values for our function. We have defined values because we can input anything in x and we'll get a certain result. So from here we'll get a certain result. But we always have this special point because there our function takes a different shape, and we want to know when that shape changes, do we still keep the graph intact or do we have a gap? So the signal in the mind is that we have to check continuity at the special point. Check at special point. And remember the criteria. The criteria is that we want to have the limit of x approaching that value from the left. So the limit that x approaches 1 from the left side is equal to the limit of x approaching 1 from the right side, and is equal to f of 1. Now what matters here is to understand which shape we're going to use for f of x. So when x approaches 1 from the left side, that means x is coming from below 1, from less than 1, so we're using this shape. When x is approaching 1 from the right side, it's coming from above, so we're using the other shape of the function. And when x equals to 1, then we're using also the second shape of the function, because this includes the value of 1. So we go over here. If this criteria is satisfied, if all equations happen, then we can say that the function is continuous at that point. But if at least one of them does not satisfy, then we cannot say it's continuous. It is discontinuous. So it is discontinuous. So that's the brief outline here. And the second part of it is differentiability. So it's differentiability. Now, what is the difference between them? Just to recall briefly on the graph. Remember the following, that we can have a function that is continuous but not differentiable at a certain point. Let me zoom out so we have a better picture. Zoom out, yeah. Put it like that. So, what if this happens? Recall that we can have a continuous function that might look something like this. For instance, here, and then goes there and sharply down. We have no gap in the function. F of x, goes smoothly. We have defined values for every x. We can plot a y value for every x. But if we take slopes of tangent lines, for example, at this point, we can draw a tangent line to it and have a defined slope. A defined slope. The slope is flat here, so that would be 0. But when we have a sharp turn, we have an increasing slope, suddenly a decreasing slope. So we cannot say what is the derivative at that point. At that point, the derivative is undefined, which means that the function is not differentiable there. That's why we're checking differentiability. And the criteria for differentiability, let's recall that we have to approach the same value of this limit. When h is approaching 0 from below, basically we're incrementing our value from below. If this is the point that we're checking, the increment has to happen from the left of x. So f of x plus h minus f of x divided by h. And again, what is x plus h? We must know which function we're using. We're using the function, let's say we're checking differentiability at x equals to 1, because that's our special point. We look at our special point, and if we're incrementing x from below, it means we'll have the shape when x is less than 1. So we'll use the following function, which means that instead of x, we'll have the new input of x plus h, which is 1 plus h. I hope this makes sense. So this thing must equal to the limit when h approaches 0 from the right of f of x plus h minus f of x over h. And again, which function are we taking right now? Well, if x is approaching x from the right, basically from here, and we're checking at the point of 1, it means that the value we're looking for is when x is greater than 1. So it's this shape of the function. And I'm stressing these things because note that although we write pretty much the same formula, this Newton quotient, I think it's called, f of x plus h here and f of x plus h here are different. F of x here and f of x here are also different because we are speaking about different shapes of the same piecewise function. So let me leave it like that for this video. In the next video, we'll go on with some signals, some mental shortcuts for derivatives, Lagrange, and limits. We are done now.